Okay, so here we are for the last example of section 2.5. We're going to be taking a look at an initial value problem, essentially, for which we're going to be able to use Euler's method to be able to solve it for a system of differential equations. So let's take a look at what we have. We have a system, and you'll notice dx dt equals y, and dy dt equals negative sine x. So this is unlike anything that we've ever seen before. In terms of the differential equations, it's definitely not decoupled. It's not even partially decoupled. So we're kind of dead in the water in terms of having a solution method for this, other than hopping into Maple and hoping that it can solve it for us. So we have an initial condition as well. So this is giving me my at t equals 0. So at t equals 0, we have our x of 0 right here, and our y of 0 right there. That's my initial condition. And then that's going to give me my step size right here. And it's also telling me how many steps to take. And so this is unlike anything that we've seen up to this point. But if we take 8 steps at a step size of 0.25, and we start at t equals 0, we can calculate pretty quickly how far we're going to wind up going. So the way to do a quick calculation is, if we want to know what our final t value is, we can take our initial t value and then add the number of steps times the step size. So 8 steps at 0.25 for the step size. We can calculate pretty quickly that we're going to be starting at a t value of 0 and ending at a t value of 2. Right? So we're going to use Maple to calculate the approximate solution, and we're actually going to get a series of points. That means we don't want to just have the beginning point and the end point. We're going to set up our array in Maple so that we can do that. So we're going to be able to figure that out in Maple, and then we are going to plot, based on our little graph down here, what our approximate solution is for the direction field. Well, technically for the vector field on this guy. So let's take a look and see what we can do in Maple. So here we are in Maple, and you can see I've done a little bit of preliminary work. I've created both my dx dt equation and my dy dt equation. And all I've done is just created the dE plot for this. This is not the vector field, this is just the phase plane, so we get a sense of kind of what direction our solution curve is going to be following. And so if I started with an initial condition, like we have in our problem of 0, 2, that would put me right about here. So I expect my solution curve is going to kind of droop down like this and maybe kind of jump across and go up. But if we're running from this point forward, we know it's going to go this direction. I just don't know how far it's going to go over a time of 0 to, technically it's 0 to 2 is what we're interested in. Oops, I think I did something wrong. Oh, I need to re-enter these here. Boop, boop, boop. See, it's a problem when you copy and paste things too much. So if I do this one more time, so if we started at an initial condition there, we know it's going to go this way. We just don't know how exactly it's going to behave. It's really hard to look at a phase plane and know how long to draw the curve, because I don't know what 0 to 2 is going to require in terms of the length of the curve on here. So what we can do, though, is try to clean things up a little bit and generate, oh, whoops, I got rid of my equation. Didn't mean to do that. And generate, it keeps doing it, stop doing that. And generate my solution, my approximates, using Euler's method. So I'm going to copy and paste the code here, and you'll notice I've just grouped my equation 3 and equation 4, and there's my initial condition right there. So they're grouped together in the first clump, and then I have my dependent variables, x and y, both as functions, and I tell Maple I want a numeric solution, and I want it to be a classical method. There are other methods, but the only one that we're going to use is the classical or Euler's method. And then the output, you'll notice I'm going to create an array that actually has a whole bunch of values. I'm going to basically generate for each one of the steps. I'm going to generate a value. You don't have to. You can do you can generate as many outputs as you want along the way. And then of course I have to tell Maple the step size. So this should produce a table that has 1, 2, 3, 4, 5, 6, 7, 8, 9 rows plus the legend row. And it should give me coordinate locations. And so we've got, at each one of these t values, I have an x of t and a y of t. So I can tell just by looking at that where my coordinates should be. Now you notice the coordinates, the x and the y coordinates on here do correspond to locations on the phase plane, but this thing doesn't create a graph for us. So I'm going to take this last row because that's really where it's making the prediction that we're interested in. Where does this thing end up after 8 steps? And I'm going to hop back over to my paper and say, well, we're predicting, based on Maple, we're predicting an x value of 2.997, so really close to 3, and a y value of 0.75 or 0.76. And so if we locate that point on our direction field here at an x value of really close to 3, that's going to be, there's 4 right there, there's 2, so 3 is right here. So that's a really close to 3x value, and a y value of positive 0.759. And 0.759 is getting up there pretty close to 0.8. So I'm going to put it like right about here. So that's where I'm guessing the point will be based on what Maple has to say. Now you'll notice I've got, I can also put in our initial condition was right there. That was our initial condition. And so based on what we see, it looks like the curve might be a little bit of an overestimate, but not too bad based on what we're looking at. So let's hop back on Maple and take a look at the actual curve on a DE plot by including the initial condition. So back in Maple, I'm going to just basically copy and paste my DE plot command from above and then just add an initial condition into the mix. And let's see where we go after from t equals 0 to t equals 2. Let's see where we're at. Oh, I forgot the line color. Oh, that stupid thing. Line color equals blue. There we go. And so notice, we guessed the value would be just shy of 3. This is quite a bit shy of 3. And we guessed a y value of 0.76, somewhere in that area. So it looks like our y value is pretty accurate, but our x value is quite a bit off, right? We're guessing somewhere closer to here. And it looks like our curve is, in actuality, a little bit tighter than the curve that we predicted, which would be something like out here, right? But that's not surprising, given that our x and our y, our dx dt and our dy dt, we could take a look at those equations and take a look at the second derivative test, and that would give us a sense of whether we expect an overestimate or an underestimate, and both of them are going to expect an overestimate. So not really surprised by that, based on what we know about the original differential equations. The other thing that we could do if we wanted to is we could take each one of these x and y pairs and we could plot them as points and take a look at what we have versus the solution. And by the way, just in case you're wondering what the solution would look like, we can hop on here and say, hey Maple, will you desolve, just straight up desolve our system of equations, and in this case it would be equation 3 comma equation 4, and I just want the general solution. I'm curious what the general solution looks like. And I click on it, and I wait, and I wait, and I get something that looks like this. This, starting here, that is the equation for y of t. And as you can see, it's kind of ugly. Looks like there's 2 possibilities. And that makes sense because you could have a possibility of y of t that's up here or a possibility that's down here. And notice they really are moving in different directions. And the x of t just depends on the arc sine of the derivative of y. Ugh, what a mess. Even if we added an initial condition, or two, in this case we're going to add one initial condition, or one set of initial conditions. And if you remember, that's x of 0 equals 0 and y of 0 equals 2. The solution that we get, still not incredibly pretty. Notice, it takes Maple a little while to figure this out. This is not exactly simple. The approximations are much easier to do than the actual calculation. And we're waiting. And we're waiting. And just in case you've never noticed this before, down in the bottom corner of the screen for Maple, you can see there's a lovely little timer. It says time 37, mine says 37.37 seconds. That is basically telling me how long it would take to run all of the commands on this page. Now, you'll notice the output for my particular solution is kind of ugly. So again, this is all the output for the particular solution. So you'll notice this is not something that I would want to mess with or try to solve by hand. So solving it numerically is a pretty good substitution, a pretty good replacement for solving this by hand. I'm still going, still going, still going. This thing is really, really nasty and involves lots and lots and lots and lots of parts. Now, of course, I have my font size blown up quite big, but this is, okay, now I'm just going to scroll. This is taking forever. Holy moly. Okay, I'm just going to grab on here and go. Still going. Still going. Someday I should get to our problem. It's up here somewhere. Holy moly. Oh, there it is. Okay, let's not do that again. I mean, the general solution was bad enough. So I'm going to undo that because I don't really want that stuff in there. So this thing has a solution. It's just nothing that we'd want to take a look at. So I'm just going to politely delete that and try to ignore that I ever tried to do it. So that gets us to the end of section 2.5, which is also the end of our notes for chapter 2. We now have a method for being able to turn a second-order differential equation into a system of differential equations, first-order differential equations. We have a method for being able to solve first-order differential equation systems that are partially decoupled or fully decoupled. And then last but not least, we have our numerical method for being able to approximate solutions, just like what we're doing here. But we have to have a starting point, and we have to know how far out we want to approximate. So that gives us quite a bit of power to be able to solve, or at the very least approximate, solutions for systems of differential equations, as well as, from chapter 1, individual differential equations. We're going to move on next into chapter 3, which is going to take kind of a deep dive into certain types of systems of differential equations. But that's it for now. Oh, one last thing that I will note is at the bottom of this, I'm going to add what happens if we wanted to take a look at a system of crazy differential equations, things that we would never hope to solve analytically. And how can we use Maple to predict a value? What does it look like to use Euler's method? So there's just another example of just some crazy equations in there. So you can take a look at that. That'll be posted in the notes for you as well.